This lecture covers asymptotic analysis. Here's the roadmap of what we will cover. We will start by comparing asymptotic analysis to upper, lower, and average case analysis as two different dimensions of time complexity analysis. After that, we will cover the growth of functions, which is the foundation of asymptotic analysis. In the end, we will explore how asymptotic analysis is conducted on algorithms and summarize what we learned. We covered the worst, best, and average case analysis. This is one dimension of time complexity analysis. If you think about the time complexity analysis as an umbrella term, then the worst, best, average case analysis is one of those things that you do under this umbrella. From what we learned, we know that such analysis depends on the characteristics of the input. In contrast, the focus of this lecture, asymptotic analysis, is a different dimension of time complexity analysis. It is about describing theoretical guarantees of the performance of an algorithm, and it doesn't really care about the characteristics of the input. At its core, asymptotic analysis is about measuring how algorithms perform as the input size keeps growing. Asymptotic analysis allows us to use asymptotic notations to simplify the time complexity functions of a given algorithm and make it easier to compare the relative performance between different algorithms. So you may wonder what are asymptotic notations and how the simplification works, and how the two dimensions, the worst, average, best case analysis and asymptotic analysis, are related. We will answer these questions one after another as we move forward. So let's dive into the growth of functions next. Growth of functions is the foundation of asymptotic analysis. Before we get into the details, here's a taste of what we will try to cover and define on this topic. We will try to define the upper and lower bound of a given time complexity function. These can help us simplify the efficiency of that time complexity function as the input size grows. We will map them to the symbols, as you can see on the screen. The upper bound will be denoted using big O and the lower bound using omega. Sometimes a time complexity function happens to have the same upper and lower bound. In that case, it will be denoted using theta. So let's introduce the formal definitions of the upper, lower, and the tight bound one after another, starting with the upper bound. So here is the formal definition of the upper bound. The definition is written using a lot of math symbols. Let me help you decipher them in case a symbol is foreign to you. So all the symbols that might be foreign to you have been circled out, and their corresponding meanings are all made explicit. For example, the symbol like a reversed E says there exists something. The symbol like a V with a horizontal bar crossing in the middle says for any. Remember, this is the definition for the upper bound given a time complexity function. So this definition essentially says that given a time complexity function fn and another function gn will be the upper bound of fn if there exists two constant numbers to sustain a relationship between fn and gn. So what are those two constant numbers? First, you need a number c. Of course, c needs to be bigger than 0. Second, you need a specific input size n0. Yeah, as you can imagine, because n0 represents a specific input size, it has to be bigger than 0. So what's the relationship between fn and the gn? As the input size grows and it becomes bigger than n0, fn will always be smaller than or equal to c multiplied by gn. If this relationship holds, we will say that gn is the upper bound of fn. And this relationship will be expressed using big O notation, essentially by writing big O then followed by a bracket that wraps up Gn. Okay, so this relationship is visualized in the graph that sits underneath the definition. The x-axis is the input size n. The y-axis represents the time. As input size n grows and it becomes bigger than n0, C multiplied by Gn will always be bigger than or equal to Fn. When n is small, there might be some fluctuations, and it's possible that Fn is, well, sometimes bigger than C multiplied by Gn. However, that doesn't really matter. All we care is when n grows towards infinitely large, what would the relationship between Fn and C multiplied by Gn be? Okay, if Fn is always smaller than or equal to C multiplied by Gn, then we'll see that Gn is the upper bound of Fn. So let's look at a few examples to help you make sense of this definition. Okay, as you can see on the right side of the screen, there's a question. Given Fn, this is a time complexity function. Given Fn as 2 multiplied by n plus 2 and Gn as n squared, can we see that Gn is the upper bound of Fn based on the definition? Okay, if we just plot these two functions on a 2D plane, they will look like this. Remember, n represents the input size, and it is the x-axis, and the time is the y-axis. Since negative n or negative time doesn't make sense, so all we need to focus on is this area, when both n and the time are positive. As you can see, as n grows, eventually Gn will be bigger than Fn, because Gn is a square function which grows much faster than linear ones. At about 3, Gn will be equal to Fn. That's where they cross with each other. After that, Gn will say bye-bye to Fn because it grows much faster. Okay, is Gn the upper bound of Fn? To answer this question, we need to figure out if the relationship between Fn and Gn meets what's required by the definition. Are there some constant numbers, like C, or specific input size n0, to make C multiplied by Gn always bigger than or equal to Fn? So based on what we analyzed, this question is not hard to answer. The constant number C can simply be 1, and n0 can be 3. So as long as the input size is bigger than 3, this Gn, I mean 1 multiplied by Gn, will always be bigger than Fn. In this case, we say that the upper bound of Fn is Gn, which is expressed as what you can see here. Now you see that we can use the definition to help us determine if a function corresponds to input size n is the upper bound of a given time complexity function. To make sure we are on the same page, let's look at some other examples. Okay, so on the screen, you can see a new example where Fn stays the same, but Gn is updated to just n. The question stays the same by asking if Gn is the upper bound of Fn. You may be tempted to say no, because as it stands now, Fn seems to grow faster than Gn. Both of these two functions are linear. But the slopes of Fn is steeper, which means that it grows faster. However, that's not how you are supposed to answer this question. The key to answer such questions is to stick to the definition. In other words, as long as you can find two constant numbers, C and n0, where n0 represents a specific input size, okay, then when the input size grows beyond n0, Fn will always be smaller than or equal to C multiplied by Gn, then you can conclude that Gn is still the upper bound of Fn, regardless whether Gn in its current state grows more slowly than Fn. So instead of plotting these two functions directly, can we start by trying to find some constant numbers to make this work? Can we find a constant number c to make c multiplied by gn grow faster than fn? Well, actually, any number bigger than 2 should work. This is based on what you know from math. For example, we can make c as 5 and n0 as 1, and plot both fn and c multiplied by gn on a 2D plane. As you can see, c multiplied by gn grows much faster now, and it crosses fn at some point where n is smaller than 1. So any input size bigger than 1 will guarantee that c multiplied by gn is bigger than fn. As a result, we can find two constant numbers to sustain this relationship between fn and gn. We would say that the definition is being met, so we can conclude that gn is the upper bound of fn, which is expressed as fn belongs to big O of n. From this example, you can tell whether the given gn grows faster than fn doesn't really matter. It doesn't determine if gn is the upper bound or not. As long as c multiplied by gn grows faster than fn, it will be good enough to deem gn as the upper bound. Whether c is 5 or 10 or even 100, it doesn't matter. Okay, let's look at another example. In this example, the question stays the same, but fn and gn are different. So both fn and gn are square functions this time, but fn has more terms, such as 3 multiplied by n and 9. As it stands now, fn does grow faster than gn because of the extra terms. However, from the first two examples, you know that this comparison doesn't matter to some extent, as long as you can find another constant number c to make c multiplied by gn grow faster than fn, gn will be the upper bound for fn. For example, we can make c as 2. So c multiplied by gn will be 2 multiplied by n squared, which grows faster than fn. Considering the extra term in fn, I mean 3 multiplied by n plus 9, when the input size n is small enough, it is still possible for fn to be bigger than c multiplied by gn, such as 1 or 2 as the input sizes, which would require you to set this n0, the specific input size, accordingly and carefully. We can make it big enough to account for the early fluctuations. We can make n0 like 100. Given these two constant numbers, we can plot fn and c multiplied by gn. Okay? All we care is the area where input size n and time are bigger than 0. As you can see, c multiplied by gn grows faster than fn, and they will eventually cross with each other, while at the input size of about 5. After that, c multiplied by gn will always be bigger than fn. As a result, c as 2 and n0 as 100 can help sustain this relationship between fn and gn. So you can say that gn is the upper bound of fn, and you can express that as fn belongs to big O of n squared. From this example, you can see that some time complexity functions may have multiple terms being concatenated using plus. In those scenarios, all you need to care actually are the terms with the highest degree of the polynomial, or say the leading terms. The other terms with the lower degree of polynomial, or the other terms that grow comparatively more slowly, they don't matter that much when it comes to determining the upper bound. Okay, so now we have seen and cracked 3 question examples. Let's move to a different set of questions of different flavor. Like this one that you can see on the screen. It asks you to prove the given time complexity function Tn's upper bound is big O of n. So Tn is a linear function defined as 8 multiplied by n plus 5. To prove this, we will stick to the definition of the upper bound. To cast the upper bound definition to this question, all we need to do is to find a constant number c and a specific input size n0, so that 8 multiplied by n plus 5 will always be smaller than or equal to c multiplied by n when the input size n is bigger than n0. We know that the coefficient in a linear function determines how steep its slope is. In the given time complexity function, the coefficient is 8. To make c multiplied by n steeper, or say grow faster, all you need to do is to make c bigger than 8. You can make it a 9, for example, or 10. For example, we can go with c as 9 and find the n0 accordingly. In this table, I list a few values of n. When n is 5, it will make 8 multiplied by n plus 5 equal to 9 multiplied by n. Any numbers bigger than 5 will make 9 multiplied by n bigger. That said, we can choose n0 as 5 or anything bigger than 5, such as 6 or 7, as is listed on the screen. The logic to prove this question is to subtract 8 multiplied by n plus 5 from 9 multiplied by n. Then the remaining would be n minus 5. It will always be bigger than or equal to 0 as long as n is bigger than or equal to 5. That said, we have successfully proven this. Well, the trick is just to find those two constant numbers to sustain this relationship between Fn and the Gn, as is in the definition. The question comes with a different style, or different flavor, by asking you to prove a time complexity function has a specific upper bound. The key to solve this type of questions remains the same. All you need to do is to stick to the definition of the upper bound. As long as you can find a constant number c and a specific input size n0, so that the given time complexity function will always be smaller than or equal to the upper bound function multiplied by c. Of course, when the input size grows beyond n0, you will be able to verify their relationship and solve this type of question. Now you have seen enough about the upper bound. Let's move to the definition of the lower bound. Okay, so this is the definition of the lower bound. It's similar as the upper bound. The symbols that might be strange to you have been marked out again. The definitions says given a time complexity function Fn and another function Gn, if you can find a constant number c and a specific input size n0 to sustain a relationship between Fn and the Gn, then Gn will be the lower bound of Fn. So what's the relationship? Fn will always be bigger than or equal to c multiplied by Gn when n is bigger than or equal to the specific input size n0. Okay? Gn being the lower bound of Fn is expressed as Fn belongs to omega of Gn. The visualization sits below the definition. As you can see, the x-axis represents the input size n, and the y-axis represents time. As n grows beyond n0, Fn will always be bigger than c multiplied by Gn. Again, the fluctuation when n is smaller than n0 doesn't really matter. Even if this n0 is very big, such as 1 million or 2 millions, as long as it is a constant number, it will be fine. To make sure we are on the same page, let's look at a question example. So the question asks if the given Gn is the lower bound of Fn. Fn is defined as a square function, n squared plus 2 multiplied by n plus 3. Gn is defined as 10 multiplied by n. To directly plot these two functions on a 2D plane, you will have this. the two functions, they will cross with each other at an input size of about 8. After that, as the input size grows, Fn will grow much faster than Gn. To determine if Gn is the lower bound of Fn, all we need to do is to plug in the definition of lower bound. If we can find two constant numbers c and a specific input size n0 to sustain this relationship between Fn and c multiplied by Gn, we will be able to conclude that Gn is the lower bound. Based on what you see from the plot, based on what you see from this visualization, it's not hard to find such two constant numbers. For example, c can simply be 1, and n0 can be 8. When n, as the input size, grows beyond 8, c multiplied by Gn will always be smaller than Fn. As a result, you can conclude that Gn is the lower bound of Fn, expressed as Fn belongs to omega of 10 multiplied by n. Okay, wait a second. Is the coefficient 10 inside omega necessary? Can we simply remove it? Well, yes, you can. In that case, you are actually trying to establish the relationship between Fn and the different function, which is simply n. We change the constant number c from 1 to 10, we don't even need to change the plot at all. Beyond this question, it's actually very rare to include coefficients in the expression of upper or lower bounds, simply because they don't matter. If a function with coefficient is proven to be a lower or upper bound, its variation without the coefficient, or say with the coefficient value as 1, is also a lower or upper bound. That's the takeaway from this example. Okay, now let's move to the next definition, the tight bound. The tight bound is defined as follows. Let's mark out the math symbols and their meanings. The definition essentially says that, given a time complexity function Fn and another function Gn, if you can find 3 constant numbers, note that 3 is no longer 2, different from the upper or lower bound. You need 3 constant numbers now, c1, c2, and n0. To sustain a relationship between Fn and Gn, then Gn is the tight bound of Fn. What is that relationship? When n, the input size, is bigger than or equal to n0, Fn will always be sitting between c1 multiplied by Gn and c2 multiplied by Gn. By that, I mean Fn will always be bigger than or equal to c1 multiplied by Gn and smaller than or equal to c2 multiplied by Gn. Okay? So the visualization of the relationship between Fn and Gn may help further make sense of this definition. C1, C2, and N0 are 3 constant numbers. When n is bigger than n0, you would always have this sandwich-like relationship, and Fn will always sit in the middle. Let's look at an example to help you make sense of the tight bound. The question is similar to what you have seen. It's asking if the given Gn is the tight bound of Fn. Both Fn and Gn are square functions. Fn is defined as 2 multiplied by n squared plus 2 multiplied by n plus 3. Gn is defined as n squared. To determine if Gn is the tight bound of Fn, all you need to do is to find 3 constant numbers, 2 coefficients c1 and c2, and 1 specific input size n0, so that they will sustain this sandwich-like relationship where Fn sits between c1 multiplied by Gn and c2 multiplied by Gn. Based on what we know from math, given a square function, the coefficients of the square term can control how fast this function grows. The bigger it is, the faster it grows, and vice versa. If we want c1 multiplied by Gn to grow more slowly than Fn, we need to make sure that c1 is smaller than this coefficient of 2, because that is the coefficient used by Fn. Similarly, we can make c2 bigger than 2 so that C2 multiplied by Gn will grow faster than Fn. That said, it's not hard to find three constant numbers. For examples, we can make C1 as 1 and C2 as 4, and plot Fn C1 multiplied by Gn and C2 multiplied by Gn accordingly. And as you can see here from this plot, as the input size grows, C2 multiplied by Gn will eventually cross Fn at the number input size about 3 and grow much faster afterward. In contrast, C1 multiplied by Gn will always grow more slowly than Fn. That said, you can easily set a specific input size, such as 10, to sustain this sandwich-like relationship. That said, Gn is a tight bond of Fn. You can express this relationship as Fn belongs to theta n squared. From this example, you can see that if the terms of the highest degree in two functions have the same degree, they will be each other's tight bond. The extra terms with smaller degrees or that grow more slowly, they don't really matter. If you think about all the examples we have examined for upper, lower, and the tight bond so far, if a time complexity function has multiple terms, only the term with the highest degree, or the term that grows the fastest, matter the most when it comes to determining the bonds. That's actually how bonds help simplify the measurement of growth of functions. Now, we have wrapped up all the definitions of upper, lower, and tight bonds. We are done with the growth of functions. We will move to asymptotic analysis next. So what's asymptotic analysis about? It's about combining what you have learned from the last two lectures and this lecture. Given an algorithm, you will be asked to find its upper or lower bound, or sometimes tight bond. For example, this is an algorithm that we examined in the first two lectures. This algorithm searches for and returns the max value, given a linear data structure like an array. In the past, we analyzed its best case and worst case, and derived time complexity functions accordingly. We know that regardless of whether you're talking about the best or worst case, its time complexity function will always be a linear function of n. Based on what you learned from growth of functions, you need to apply the definition of bonds and identify its upper, lower, and tight bond. That's what asymptotic analysis is all about. Okay? So for a linear time complexity function, both its upper and lower bound can simply be n, expressed as big O of n, or omega of n, expressed as big O of n and omega of n. In case you wonder if you can say that the upper bound of this algorithm is big O of n squared, yes you can, but that won't be as accurate or say as tight as n. Similarly, log n can be the lower bound of this linear function, but won't be as tight as n. Okay? When you apply the definition of tight bound, it won't be difficult to find its tight bound as n. So we pretty much skipped the steps of applying the definitions of bounds because we have just seen very similar examples. However, this example still tells us something about asymptotic analysis. Given an algorithm, you need to analyze its best and worst case to derive time complexity functions first. From there, you need to determine the bounds based on the derived time complexity functions. Okay, that's what asymptotic analysis is about. So let's look at another example, insertion sort. We analyzed this algorithm in lecture 2. In case if you need a refresher, the link to lecture 2 is in the description. So we analyzed the worst case for insertion sort and derived a time complexity function as a square function. The upper bound for the square function can be simply another square function with coefficient as 1 and no extra terms. We have seen how this works. when we covered the growth of functions. Such an upper bound can be expressed as big O of n squared. In case you wonder, well, if n cubed is also an upper bound of this time complexity function. It is. It's just not as tight as n squared. You can also deduce its lower bound and a tight bound, which will both be n squared. Okay? However, it's worth pointing out that the upper bound of the worst case time complexity function is also the upper bound of this algorithm. Because other cases, I mean the best case or the average case, are more efficient and it takes less time to execute. So there's no chance for other cases to go beyond the upper bound of the worst case. As a result, you can think it as the upper bound of not only this time complexity function of the worst case, but also this algorithm. Okay? Similarly, we also studied the best case of insertion sort and derived its time complexity function, which is a linear function. The lower bound of a linear function can just be another linear function in its simplest form, which is n. Okay? Similarly, its upper and tight bounds can also be the same linear function, which is n. The lower bound of the best case is what we should pay attention to. It is expressed as omega of n, and it's not only the lower bound of the best case, but also the lower bound of the insertion sort algorithm. The rationale is similar as the upper bound of the worst case. No other cases are more efficient than the best case. If the best case doesn't go below its lower bound, neither would other cases. As a result, the lower bound of the best case is the lower bound of the algorithm. So from this example, we can see that although best case, average case, and worst case analysis is a different dimension from asymptotic analysis, they are still related. The relationship is somewhat self-explanatory. If you're looking for the upper bound of a given algorithm, go for its upper bound of its worst case. If you are looking for the lower bound of a given algorithm, go for its lower bound of the best case. Now, you should have a better and clearer understanding of the two different but related dimensions of time complexity analysis. The last thing we need to talk about under asymptotic analysis is the comparison across common upper bounds. Yes, upper bounds are typically what we care about the most because they measure the worst possible performance of algorithms. Some of the commonly used upper bounds are listed here on the screen, such as log n, n squared, and 2 to the power of n. If you plot all of them to a 2D plane with the input size as the x-axis and the time as the y-axis, you will be able to see which one is more efficient and which one is slower. For the record, because we seek efficient algorithms, as the input size grows, the less time an algorithm takes, the better. For example, log n grows much slower than n. So if an algorithm runs on big O of log n, that's great for us. In contrast, if an algorithm runs on big O of 2 to the power of n, that would be terrible. In case if you forget or have difficulty comparing two different upper bounds, you can always find some concrete numbers and plot the dots first, then concat them using lines. For example, a series of good input will start from 1, then multiplied by 2, such as 1, 2, 4, 8, then 16, etc. After calculating all the corresponding values using upper bound functions, you will have a series of dots. When you concat them using a line, you will have a rough picture of its growth rate. So if you have difficulties in memorizing the different relationships among these upper bounds, it's actually not needed, as long as you know how to get the job done. In this lecture, we compared asymptotic analysis to upper, lower, and average case analysis as two different dimensions of time complexity analysis. We also covered the growth of functions and explored how asymptotic analysis is conducted on algorithms. Hope you learned something new.